Just briefly, if everyone can pay attention to the fire and health and safety slides, so you all know which way to run in case we set on fire tonight. Okay, thanks all for coming. This is the first annual, hopefully, Early Careers Evening event that we'll have as part of the engineering group. Hang on a sec. Right, back to the original slide. So, and the idea is really just to provide a platform for young early careerist engineering geologists, both from consultants, contractors, and also from academia. And it's really about giving people a platform to speak and practice public speaking. So we'll run through the different presentations. Everyone's got 10 minutes or so. We're not going to have a Q&A session tonight, but what we will do is encourage everyone to stay for the post-meeting drinks afterwards that have been sponsored by Mott and Arup. And then you can ask your questions there to the speakers as and when you want. So just to kick things off, I'm going to start. Once I've got my slide. I'm going to talk to you about some work in Kazakhstan that I've been working on before Christmas, and it's all to do with socioeconomic sustainability. And we're working on the Karachaganak expansion project, and the client was KPO, Karachaganak Petroleum Operating BV. So really, the main part of our work was all to do with elevating local skilled resource, so localizing the supply chain in terms of providing our client with a local contractor that could do the work to the standard that they required. And this was all brought about more than 10 years ago when the local government basically put in place local content restrictions in terms of forcing our client to employ locals to do certain jobs. And so the way in which we went about elevating that local skilled resource was by, first of all, selecting the contractors to match the processes that we were doing, so making sure we had a GI contractor in place that we thought we could use and assessing their skill set, and then modifying their tools and equipment to make sure that they could conduct the testing and sampling that we required on site. And then stuff that we're still doing today, which is what I was involved in before Christmas, which is on-the-job training, so knowledge transfer and conducting workshops. So for those who don't know, Kazakhstan is in Central Asia, denoted here by the yellow. And the project that I was specifically working on in the Karachaganak oil and gas field was just next to Aksai in the northwest, right next to the Russian border. So a few details on the project to start with. It's a consortium of E&I Group, Shell, Chevron, Lukoil and Kazmunai Gas. The site is a processing facility located in one of the world's largest gas and condensate fields. And our role, which has been over the last 10 years and up till recently, a technical advisor for pre-feed, front-end engineering design and feed of all civil and ground engineering activities. And the structures we were kind of looking at developing and understanding of the ground conditions for was processing units, gas reinjection stations, power plants, waste management units and associated supporting infrastructure such as pipelines and roads. So the bottom line really in terms of us not only training the contractor and getting them to be able to work to a standard which is internationally recognised was their factual report at the end of the day. The main reason being that this would be the key deliverable for the client to supply to an EPC contractor who's going to be tendering for the construction of the work that we're looking at. And so if they don't have a decent factual report that they can completely understand the associated risks with the grounds, then they're not going to provide a coherent set of tenders back, and the client's not going to be able to differentiate between them well. So that's really the added value we bring is to, although we're not contractually obliged to, try as much as we can to ensure the quality of that report. And obviously the main way we'd normally do that in the UK would be biannual supervision and checking of that report and making sure it adheres to the local standards and the technical specification. But like I said earlier, it's about modifying their equipment and plant so we can take the samples that we want, conduct the testing that we want, but then also on-the-job training with their staff. And so the equipment that we kind of modified with them and helped develop, which didn't previously exist in Kazakhstan, so they didn't have sampling tubes so they could take undisturbed samples. They didn't have hydraulic extruders, which we'd had to design and then locally procure as well from other Kazakh firms. And we also designed and locally procured a modified CBR mould. But the work I was more involved in before Christmas for the GI was basically being on site with their geologists and helping them to log to not just GOST, the local Russian standard, but to help to adapt it so that then it could be interpreted on an international kind of playing field. And so, because we were auguring between 2-metre spaced undisturbed samples, you know, a lot of these guys would just have a look at what came up and just go, oh yeah, that looks the same as it was before. So in order to get them to log it a bit more frequently, so you get greater resolution in the logs, we're getting them to take undisturbed samples, which we weren't testing, we were just getting them to destructively log it, and it also helped to improve their description based on what we were telling them, because they're logging it twice as much. And really, the key thing with this material is that it has a lot of additional components in terms of carbonate nodules, gypsum inclusions, and organic material. And some of these additional characteristics can be used to cross-correlate across the site. And if they're not getting picked up in the logs, then then we're not really getting the detail that we need. And so that was part of what we tried to get them to improve. So here's an example of one of their logs before we got involved with them, about over 10 years ago. And this line here is actually just one borehole that's 15 metres deep. And you can see the description's just one description. It's also a pretty poor description, if you read it. Brown, compact, lumpy, doesn't sound like soil, does it? With gypsum inclusions and limestone balls. So they're not really using terms, and albeit, to be fair, it might just be a translation issue, but it's part of our job to make sure that we're conveying it in a way that is technically understood for people who work within our profession. And so, giving you an example of something that we kind of help them to produce, this is 15 metres, so you know, not just one description, they've subdivided it into 5 components, and they're describing it in a chronological, coherent manner, so primary soil type first, secondary component next, colour, the consistency or strength, and then describing the additional components in a way that we would understand in terms of British standards. So describing the frequency of the inclusion in terms of occasional, and then the size as well at the end. And it sounds simple and basic, but it was actually like pulling teeth trying to get these guys to do this. And I don't know if you can read, but generally they describes some fine soils as loam, which is not a term we usually use in British standards. And so that was a big kind of issue we had on the logs in terms of getting them to adhere to the Russian standards, but then providing a note at the bottom to explain exactly what that material type was on an international kind of playing field. So when we compare Russian standards to British standards, the kind of 2 key things that we struggled with on site were their descriptors for flow index and how they compared to our consistency terms or strength terms for British standards. And you can see that not only are they different, but also that they apply to different ranges of stress. So having that cheat sheet was really useful on site to be able to quickly check log what they were producing and agree with their geologists. The table on the left here is basically outlining the different types of fine soils that they classify their material as, loam or clay, and that's determined basically in relation to the plasticity index range of the material. So fairly similar to how we describe fine soils in the UK, but loam doesn't really equate directly to silt, and clay doesn't directly apply to clay, because obviously we define our fine soils based on where they plot on the A chart above and below the A line. And so we had to work on site to get them to understand the way we logged it in our hand tests, and then try and find a meeting point in terms of an approximate descriptor. And this is obviously just preliminary. The lab testing would affect those descriptions later on. So then, just to kind of show how much this work actually does matter, it sounds like we're just banging a drum, but this is data from about 10 years ago. So it's kind of showing the pre-training versus post-training percentage increase in the fieldwork and laboratory testing that the local contractor was able to win. So this graph on the left, shows percentage proportion of the post-training actual input versus the pre-training equivalent, so what they were running before. And you can see for the exploratory holes, that's gone up about 55%, lab testing 65%, and field testing and high-quality sampling, which were the tools that we kind of helped develop with them previously, that's gone up at 100%, so quite a large impact there. And in terms of the man-hours that they were able to increase their workload by, I was up by 20,000 man-hours for the year of 2008. So quite a large impact from the training we'd done with them and the quality they could provide the client in the end. And finally, just to finish off, this is a tender assessment that we did before we conducted the ground investigation towards the end of last year. And we, along with some other consultants, assessed them. The criteria was set by the client, but you can see that the contractor Kerg, who are in blue there, consistently score top marks and well above the mandatory score, and are kind of beating their opposition quite significantly. So it shows the kind of long-lasting impact that our training has with them, and their ability to maintain the quality that we require. I'll now pass on to Rachel Garside of PetroLab, who's going to talk to us about her last 4 years working within applied petrography.
So today I'm going to talk about my experiences in applied petrography so far. Now, I should probably start with explaining what applied petrography is. It's the petrography of geomaterials, so using the skills that you might have learned at university for looking at rocks and applying it to things like concrete, mortar, building stone and aggregates. This is actually my first real geology job since I graduated, and I've been there for 4 years now. I actually almost didn't apply for the job because I didn't fulfill all the criteria, and then I was rejected the first time. So I got a phone call out of the blue 6 months later saying, "I don't suppose you're still available," and I was, so I'm now there. A lot of the time it's been sort of felt like being thrown in on the deep end because I haven't actually had very much formal training. So sort of as soon as I arrived, it had been about 2 years since I graduated university, and they were like, "Okay, yeah, you need to know what all these rocks look like." And again, with the concrete petrography, I'd had a vague idea of what concrete was, but then about 9 months in, my boss put some thin sections in front of me and said, "Yeah, look at these down the microscope and look at the format of the previous reports to see what you're looking for, and then come to me with any questions." So a lot of applied petrography does rely very heavily on microscopes. About a year in, my boss brought me up to London to join the applied petrography group, which is a sort of subgroup of the engineering geology. And it's very interesting because you hear about other people's work in the area, and particularly sort of people who have slightly different specialisms. The only thing I don't quite enjoy so much is the sort of the 4:30 a.m. start to get up from Cornwall to London on time. We're a very small business, so although we've moved from four full-time staff to 8 full-time staff while I've been there, so you have to be multidisciplinary. So I'm also trained in use of making of thin sections and ore petrography for minerals, and also the scanning electron microscope for the mining jobs. But by this point, it was quite daunting because about 2 years in, I already had to start to deal with clients and start training up some of the junior staff. So it's sort of the benefits and also slightly different working at a small business. So that's an overall introduction to some of the work that I do. So these are some examples of the things that I've been involved in. The Mundic issue is an issue for the southwest mainly because they had, as a product of hard rock mining, they had all this spoil waste hanging around. And when they started to make concrete blocks, they decided, oh, this is really nicely sized aggregate. Let's put this into concrete blocks. The problem is a lot of this material has sulfides in it, pyrite, chalcopyrite, and the sulfides can oxidize and create sulfuric acid, which can eat at the concrete. The other problem is a lot of these are low-grade metamorphosed mudstones, which split open really easily and are sensitive to water, and that can also cause the concrete to degrade. So you've sort of got some nice lead ore processing waste that isn't in particularly good condition over there. This is the Bridged Institute just north of Redruth, which has got terrible cracking. That's got a nice date of 1926 up there, so you know exactly when the culprit was. So the mortgage lenders aren't very happy with that. So sort of as a condition of getting a mortgage, you have to have an all-clear concrete screening test, or the first stage is a lot of the concrete that you get it's just granite or limestone or something like that. So that's all okay. If you've got mine waste, it can then go for a further examination, and some of the areas that have mine waste, it will be fine, and there won't be very much dangerous material, and that can also get the all clear. But when you've got stuff like this, yeah, that's not so good. Now, a lot of the Mundic concrete was built in sort of the 20s and is still okay. This material was built in 2007. And you can see here, sort of, basically, you can see the edge of all the concrete blocks. And then they had an engineer on site that said, yeah, your concrete blocks are crumbling. So they said, well, can you find out why? And we looked at it, and it looked like the mine waste. Problem was, this had pyrrhotite in it, which is an unstable form of pyrite. So it's sort of an accelerated version of the Mundic weathering. And yeah, you can just see this terrible, terrible cracking through all this. It's impregnated with fluorescent yellow dye, so you can see the cracks really well. Now, a lot of the time we have quite small projects. This was a very big project. We gave a quote out for 40 samples in 5 weeks, and they came back to us and said, we've taken 110 samples, but we need the same turnaround. So that involved quite a lot of Saturday working at the end of last year. But it was the first fire damage that I'd really seen in my job. And petrography is very useful with fire damage because you get specific petrographic markers that tell you the temperatures that the concrete has got to. So this sort of red staining in the binder is a 300 degrees C. So it is quite useful. This was a quite nice one because we had concrete before from Plymouth in an intertidal zone. So we knew pretty much what seawater attack looked like. So when they rang us up and said, oh, we've got all this white material that's forming around the limestone, I sort of had my suspicions. And they proved to be correct when they turned up. So there's quite a few various salts in here. There's thormazite there, there's calcite, there's brucite, and there was also gypsum in these nice white rims as well. Quite a lot of the interesting stuff we've had has come from Ireland. So this was material that they'd laid in bitumen, and they told us, when it's getting rained on, it's just dissolving. So we said, well, send us some samples and we'll have a look at it. And when you immersed a flat surface in water for 24 hours, it ended up looking like this. So we knew there was something very wrong. So once we'd made the thin section, we realised this stuff was basalt. And at that point, alarm bells started ringing because about a year before, we'd had some material just for sort of geotechnical work, ground investigation, where we'd just done a petrographic description. Some of them came back like this, and some of them came back like this. And the problem is with some of these antrim basalts is that they're really weathered, so they've got alterations of the original minerals into these swelling clays. And then they've also full of vesicles, which are the bubbles in the lava. And they also fill with swelling clays, so you sort of got really bad water-sensitive basalts in some cases. So, I mean, I don't know what happened as a result of that. They probably just had to pick it all out again. You can't really talk about Ireland without touching on the pyrite problem. So this is an issue very specific to the Dublin area, which is mainly sat on carboniferous limestones. But the carboniferous limestones are interbedded with with mudstones that have got loads of rhomboidal pyrite in it. This is a nice image of what rhomboidal pyrite looks at high magnification. And this rhomboidal pyrite is, again, a very unstable, reactive form of pyrite. And they were finding that they had this stuff in the hardcore under the houses, and they'd also put it in the concrete blocks. And they were finding sort of walls were bulging and countertops were lifting up. You couldn't open your doors anymore because the floor had heaved. And the problem with this is that rhomboidal pyrite was oxidizing, and it was creating all this expansive gypsum growth, and there was a volume increase, in some cases about 24%. And this is a reflected light image. It's not shown up very well, but it's sort of all these iron oxide rings on the pyrite grains. The other problem was, of course, they'd used this in some of the concrete blocks as well, so you sort of got a double whammy in some cases, that you had a heaving floor and also got sulfuric acid from the oxidation of the pyrite attacking the concrete, and then you also had internal sulfuric acid attack from the dodgy aggregate. And this is just the sort of another way that we use. So a lot of the time we use our optical microscopy, but in some cases it can be useful to have an electron microscope as well. Particularly in this case is the thormazite problem on the M5 bridges. Now what they did was they excavated this clay, and of course this clay has pyrite in it, and this is causing really bad attack on these concrete pillars and foundations. So Thaumasite, you can usually see it in thin section when it's in cracks and voids, but if it's in the binder, it's not so easy to see, and because it has this sort of wispy structure here. So in this case, the SEM is very useful because you can assign a composition and then map out pixel by pixel like what we've done here, and you can see this sort of shows where the Thaumasite is sort of filling in the binder really well. So that's sort of a summary of some of the work that I've done in the past 4 years. I like the applied petrography because it sort of uses the skills that I learnt at university in a slightly different way. And I also like the detective work aspect of it, particularly sometimes if you've had a completely unrelated job in the past and it comes in useful. And sometimes it's good to have a good memory or to be able to refer back to previous jobs. It's also exciting to be part of a rapidly expanding business. And because it's quite a small niche area, there's not too many standards to keep up with and that sort of thing with any changes. So I hope this has been a sort of brief snapshot, and thanks for listening.
Thanks very much, Rachel. That was really interesting. Now we'll have Charlene Ting from Arup.
I've got a video. How do I play that?
Try and press next. I'll check.
Okay, thanks. Good evening. My name's Charlene Ting. I'm a geologist at Arup in London. So just an introduction, I joined in September 2013, and over the past 4.5 years, I've worked on a range of projects. But tonight, I'm going to talk about one of the more exotic projects I've got in Tajikistan. I hope that's the right button. Good. So Tajikistan is in Central Asia. It's bordered by Uzbekistan, Kyrgyzstan, Afghanistan, and China. It's mountainous. So over half of the country is over 3,000 meters above sea level, and it has lots of glaciers and mountain rivers. So obviously prone to flooding, earthquakes, landslides. The red and green dots I'll come back to, but they're the bridge and flood protection infrastructure that the World Bank asked us to review. The majority are in the eastern part of the country called the autonomous Gabal region in the Pamir Mountains. We travelled along the M41 highway, aka the Pamir Highway, which is used as part of the Silk Road trading route and is currently still the trade route for Tajikistan to China and Kyrgyz. So it's constantly busy with Chinese lorries. It's the only road that connects the Gabal region to the outside world. So it's a pretty significant piece of infrastructure regionally and internationally. So this is where my video might not work. No, it doesn't. What do I do? So I became involved in Arup's Tajikistan projects in 2015. Is this going to work? Cool. Fingers crossed. Well, there we go. Well done. No, it doesn't need sound. Imagine some loud rumbling. This happened in 2015. I was a graduate at the time, and I was reviewing photos and videos of this that happened in one of the villages in Gabal. This was actually the second pulse. The first pulse had already ripped through the village. It formed a debris dam this side of the river, and that formed a new lake. The government raised a state of emergency, and Arup was commissioned by the World Bank to go and support the rapid risk assessment team. There was concern that if the debris dam was breached, flash flooding would be triggered downstream into the main town of Horog, main town in Gabal called Horog. There was also a power plant nearby, and the people filming this are actually on the Pamir Highway. So, in 2016, Arup was commissioned again by the World Bank to review some bridges and flood protection infrastructure across the country. The first part of the project started in 2016 and involved collating hydrological and meteorological data from the locals. And we carried out 2 site visits to the country, of which I was part of the second one in June 2017. The second part was a hazard assessment and developing a glacier monitoring database with the University of Zurich. And third was to provide recommendations to the World Bank and the government of Tajikistan on how to improve their natural hazard monitoring and also reconstruction of their critical infrastructure. So my role in the project team was down here. I supported a range of specialists doing GIS work, I've actually lost track of what I said. Compiling historical satellite imagery, so the declassified American spy images from the Cold War, digital elevation models, doing some GIS analysis, I'm probably sure I said that already, and assisting my senior geologist Jason Manning in the natural hazard assessment. So first part of the project, I'm just going to show you some cool photos from the site visits and some of my observations. So this bridge was one of the better looking bridges we went to see. The deck was pushed off the abutment by the sheer force of the mud flow coming through it. And that was 2 years ago, 3 now, but they thought it was still functional. So the western and eastern Pamirs, there's a bit of a difference. When we drove along the Pamir Highway in the western Pamirs, sort of looked like this from our vehicle, and is characterized by high mountain relief, rapid rivers, and most of the settlements or exposures concentrated on the alluvial fans in the narrow valleys in the tributaries of this big river here called the Pan, which is the border between Afghanistan and Tajikistan. So combine that with heavy snowfall in the winter, increasingly hot summers, increased meltwater. The main hazards in the western Pamirs are landslides and mudflows. And actually the word Pamir refers to the broad valleys surrounded by mountains, which is what you're seeing in this photo. Over here, the rivers are quieter, meandering, often dry channels when we went there in the summer, and wide open valleys where the main hazards are flooding and frozen ground. Other things we got up to on the site visit, our hydrologist in our team inspected the hydrological gauging stations and the meteorological stations up there. We carried out bridge inspections. As you can see, most of them are not in great shape, and there wasn't any scour protection and definitely no inspection reports available to look at. And senior geologist Jason here used his Russian language skills and interviewed some locals about past flooding events. On to the second part, which was to assess the key hazards at each site using a combination of GIS tools, satellite imagery, historical mapping, and our own field observations. So one of the outputs from my GIS work was the catchment analysis, which is this bold black line here for each site. We sent this off to the University of Zurich to develop their glacier monitoring database, and they found that the glaciers are actually losing 0.1% of their area each year from the 1960s until now. And the second part of my job was to georeference declassified 1960 satellite images, which was more fiddly than it sounds. And particularly in this area here, which is in the upper reaches of one of the valleys we visited, you zoom into those two photos, that's from the 60s, and that's current, you can see that there is a glacial lake that's evolving. So this sort of thing's a really useful resource for identifying monitoring changes and features, often in inaccessible locations like this. And the potential concern here is that climate change would increase glacier melt, which would obviously increase the lake volume, weaken the dam that's holding it back, and trigger glacial lake outburst flood, which is a pretty devastating hazard for the downstream communities. Oh, I forgot to show that. So our climate change analysts did some work and confirmed what we already know or believe, is that summers are getting hotter and wetter. So we won't dwell too much on that, but basically the magnitude and frequency of the natural hazards that this region face is going to increase over the next few decades. And this is an excerpt from our risk matrix that we presented to the World Bank. Just a few things to draw your attention to are the huge variation in catchment areas from like about 20 square kilometers to over 3,000. Most of the hydrological data we had was of poor quality, which meant it was hard for our flood modelers to refine their models. Most of the bridges are in poor condition, as you could probably have seen from the photos, and the local population is highly exposed to a range of natural hazards from glacial lake outburst floods, normal flooding, landslides, and avalanches. Great. On to my final part of my presentation. I'm just going to quickly run through the recommendations we provided to the World Bank. So in order to improve the flood models and the peak flow estimates, we recommended they improve the hydrological and meteorological data sets, and they should really be collected at a higher frequency, ideally daily like we do in the UK. This would involve investment in local training, updating the equipment, which is currently in process. We highlighted satellite images as a really useful resource for monitoring changes in glaciers. A landslide inventory should really be compiled through field mapping, especially around critical infrastructure like the Pamir Highway. And also, we could always do with a bit more geomorphological mapping and improve our understanding of flood and mud flows. In terms of improving existing infrastructure, we recommended seepage analysis and geotechnical design for the flood protection infrastructure, improve foundation design instead of just building a new abutment in front of the old one that had failed, and scale protection and debris impact protection. The World Bank recognised that Build Back Better should be the long-term approach for resilient infrastructure. So I obviously learned a lot from this project and the site visit, and some of the key lessons that I learned were that developing countries often have data gaps, and so our project approach needs to be modified in order to find solutions to fill in these gaps. So, for example, using remote sensing, and we should always recommend improvements for how to collect data in the future. Planning and preparation was essential for future, for a big site visit like this. We travelled some 2,500 kilometres in 10 days. So, as careful logistical planning was needed because it was hard to get back to more remote places, and we had to maximise observation times at each site. Planning, teamwork and collaboration with local experts and different teams of different specialisms. And as you could hopefully have seen from the photos, there was some really fascinating geomorphology in Tajikistan and active glacial processes on a huge scale you could rarely see anywhere else in the world. So it was a really eye-opening experience. And thank you very much, and talk more during the drinks.
Thank you very much, Charlene. Now we're going to have Jill Thompson from Fugro.
Right, here we go. I would just like to say that I chose hazardous waste classification because actually in our industry, we may drill so many boreholes, or there's so much waste that we don't actually think about where it goes and what happens. So I'll just start to go through. So I kind of will start to define what actually hazardous waste is, and introduce you to the regulations that I kind of get involved in every day. But the best way to actually explain it is through a case study of one of the projects we've been part of. And I'll go through what waste strategy we actually had, and then what waste acceptance criteria and characterisation we kind of did. So the official definition by the Health and Safety Executive states that waste is considered hazardous when it contains substances or properties that might be harmful to human health or the environment. But that might not be immediate, it could be long-term effects. So it's kind of easy to know the definition, and then if you get very caught up in the regulations, right? So there are so many different regulations that it gets very confusing. Now, we, quite a lot in the UK, we wrote a WM3 technical guidance in 2015, which kind of summarises a lot of the regulations and what to do. But the UN are trying to push this global harmonised system down at the bottom here, which shows that they're trying to get everyone together globally to use the same system. So you can't just drive your waste into the next country and dump it because they've got different regulations to us. So just to kind of go through this with a case study, this is a CCGT power station, which stands for Combined Coal and Gas Turbine, up in the north of the UK, which is a lot less exciting than where everyone else seems to have gone. So it's actually quite interesting because it's a varied site. So the northwest of the site is a formal chemical works, which provided some interesting waste and soils to deal with. So the whole scope of the works, we drilled about 60 boreholes and took environmental geotechnical samples, and that alluded to about 22 kilometres of core. So that's a lot of waste to have to deal with. And kind of the geoenvironmental assessment the objective was to determine the ground contamination conditions at the site, so then we could provide more information to assist on an appraisal or the potential cost of disposal during the site development. So we designed a waste characterisation package and then went through the guidance. So this is kind of an overview of our strategy. So we started by coming up with a grid to take samples. And we knew from our desk study that actually there was an area on the site which had a petroleum plume or potential petroleum plume across the foundations. So we knew that we could take more samples there, or we could come back to it later. And then, so for each sample, we screened it for asbestos. Due to the regulations that asbestos, obviously, I'm sure quite a lot of people deal with it. It has different regulations as to how you should deal with it. So after we did this, then we did some cone and quartering of our samples across the site. So we could see where we're testing within our stratigraphy, but also at depth. So then after this, we split it into waste acceptance criteria and waste characterisation, which I'll kind of go through next. So waste acceptance criteria is kind of set up by the landfill directive in 1999 that you have different types of landfills that you can send different types of waste to. But it's actually, so you have these three types of landfills: hazardous, non-hazardous and non-reactive, and inert. And they each have different thresholds as to from different WAC tests that you can use. But obviously it's not just the solids that are a problem, but it's the leachates, as you can see here, that can create quite a lot of problem when you send it to landfill, then it can leach out over time. So when you do send it to the landfill, it's just you may not have to have a WAC test, but also the waste code from the list of European wastes, a description of the composition, and maybe the special provisions such as asbestos, as I've spoken about before. Equally, I think quite a lot of people get confused that talking about leachates and everything else, a WAC test is actually only for solid waste, and you send liquid waste into a different process completely. So in our project up north, we pre-screened for asbestos and found one positive result, which is quite impressive for the whole site. And then we further screened and found 3 samples which went over for fluoride. But actually, waste acceptance criteria doesn't tell you if it's hazardous in terms of human health assessment. It just tells you what landfill you can send it to, which is why you do the other stream of waste characterisation. So waste characterisation shows whether it's actually hazardous to us or to the environment. And the European Waste Catalogue states you must classify it as absolutely hazardous, or a mirror entry, or an absolutely non-hazardous. So absolutely hazardous would mean it would be hazardous regardless of the concentration in the soil, such as asbestos, say. Or a mirror entry is when it depends on the concentration, so metals can be hazardous at specific levels. And then absolutely non-hazardous is anything that can be completely inert. So with the global harmonised system they're trying to push it in, they provide H codes for the hazard property and a threshold to hazardous for health. So we sent 42 samples for waste classification, we'd previously provided a suite of contaminants that we'd known from our desk study. So if we found petroleum underneath the site, we should have tested for SVOX or creosoles, phenols, etc. So in our data analysis, we found that 22 samples came up as the mirror entries, so they were potentially hazardous depending on the threshold. And this came up for total petroleum hydrocarbons and toluene. So the potentially hazardous value was because of flammable liquid having a flash point below 60 degrees. So actually because considering we were dealing with soils, this actually, unless the toluene was running across the site, it was unlikely that it was going to be a hazard. However, we decided we were going to do a number of flashpoint tests across the site to see whether it was a hazard to us or not. So after this, we actually mapped everything out to see where all the potential hazardous is. So you can see at the bottom here, we had a number of samples. These two samples failed for both waste acceptance criteria for fluoride and for toluene. And then up, you found the different pockets. So actually it enabled us to plan to take more soil samples or provide a potential solution or for when they were excavating the site later. So did we kind of complete our task? I think we obviously took all the samples and did both waste acceptance criteria and waste characterization testing before deciding whether it was hazardous or not hazardous or what we should do next. So just to conclude, that actually waste acceptance criteria is for landfills and it doesn't always tell you whether it's hazardous to human health, whereas waste characterization determines the hazardous properties. And the visual mapping of this is quite interesting to show across site as to where the hazardous properties are. But equally, it makes it a lot easier if you know your guidelines.
Okay, now to hear from Tom Morgan, our only academic of the evening. So.
Good evening. My name's Tom Morgan. I'm a second-year PhD student at Imperial. I'm doing it under Dr. Richard Gale and Dr. James Lawrence, and I'm currently looking at faulting in London and how it's impacting the geotechnical community. So to just give a bit of layout to my talk, I'm going to be giving a bit of context to my research, talking about faulting in the faults itself before going into how I want to approach this research, before giving two specific examples of some of my research at the moment, before finally concluding. So this is just the current model for the London Basin, and as you can see, it's considered to be a large synclinal basin, which is relatively undeformed internally with a few discrete faults along it, such as the Greenwich fault. What we actually know is that there's faulting all across London, and these are some examples. We've known about this for over 150 years. Here's an example from, I want to make sure I don't press the wrong button, from Whitaker et al. And you can just see there's a really nice fault here, which is just cutting through chalk and paleogen sediments, and it looks like something like a drift drill hollow next to it. And this is a photo taken from the Farringdon Station Works. This is the St John's fault, which then just intersected for Crossrail. But what we're also starting to see now from major tunnelling projects, that you get zones, narrow zones up to 1 kilometre in width of very intensive faulting, which are internally highly deformed and are quite unpredictable. So this is the London Bridge fault zone, which was identified during the Thames Tideway tunnelling works. And this is originally from Tim Newman's site, but he's very kindly let me use it for this presentation. So I just think it just shows, if you go back to 2 slides ago, something which is undeformed, you're assuming intact material properties, something which you've got these localized zones which are very deformed and can have much weaker properties than their intact equivalent. And also as well, INSAR data now is being used, and it's showing that London is actually moving both vertically and laterally by millimetre rates sort of per year. And this movement isn't uniform, it's happening in a sort of block-like components. And these blocks, the boundaries of which they're pretty linear. And what we can infer from that is that these fault zones are actually controlling the movements of different parts of London. They've pretty much compartmentalised them into blocks which are moving relative to one another. And it doesn't look like, when I'm saying they're moving, it's not like an earthquake sort of thing. They're just sort of creeping against each other. It's hopefully okay. But we're also seeing that it's actually impacting its mechanical properties. So I've just put up Jaeger's single plane of weakness theory here, which just says that if you've got a discontinuity present in your rock mass, it's going to be detrimental to the strength of the rock mass. And we can actually see this in London as well now. So here are London clay undrained shear tests done for Crossrail. And you can actually see that the fault zone samples are significantly weaker than their undeformed counterparts. So faulting is like it's making the ground weaker locally, and also because it's going to be fracturing the ground as well, you're going to be having it's going to be affecting its hydrological behaviour locally as well. So now I'm going on to so hopefully I've given a bit of context to why I'm looking into faulting. This is what I want to do is I want to sort of combine structural geology with engineering geology. I'm going to look at the origin and evolution of these fault zones, and look at how they're impacting the geotechnical work done in London. So I'm going to be looking at tectonic scale processes and how they're affecting site scale behaviour in London. And now for the rest of the talk, I'm just going to give 2 examples of bits of my research. So looking at the origin of the faulting and also how I'm going to map these fault zones. So the structure of these fault zones, they look like they're the upper parts of flower structures, which are themselves, they sort of splay out from a single fault at depth. So we've got evidence from this that they originate at depth, and we've also got evidence from some of the lower sequences in London, such as the Lower Green Sands and Galt Formation, which show evidence of syndepositional fault activity. And because they lie on the basement, this evidence of these faults must have originated from the basement itself. So we've got evidence of faults coming from the basement, but what is the basement? It's actually relatively shallow under London, and we know that due to its tectonic history, there's going to be faults within it. So if you can imagine, if you've got a shallow basement beneath you, which has already got pre-existing faults, and you reactivate it under oblique stresses, you're going to be developing flower structures which are going to propagate up, and that's what we're seeing in the near surfaces as fault zones. So one thing I want to do now is, during my research, is to try and map these faults in London. But this is it's quite a problem. But it's actually quite funny. I was thinking everyone's been to all these amazing sites all over the world, and I can't even access my sites because they're all underground. And London's completely, because it's all urbanised, you can't see the faults at the surface, and because some of these materials, such as London clay, are so homogeneous, you can't see faulting within them. So it's quite a problem of how I'm actually going to map it. But what I'm going to do is I'm going to compile boreholes from across the region. I'm going to use them to create mathematical surfaces for each lithology, and use any changes in elevation across it to identify faults. And obviously not every change is going to be caused by faulting, so I'm going to use a set of criterion to constrain what is actually faulting or what other features. And now to demonstrate sort of how I'm going to approach this fault zone mapping, I'm going to use the Blackwall Tunnel, because it's an area which's got it's got high borehole coverage, and the boreholes themselves are very high quality. So if you were to assume that the entire ground was intact and unaffected by faulting, you'd affect all the lithologies to be sub-horizontal. But we can see from this ground model I've produced for it that this isn't the case. So you've got the Lambeth group, the Thanet Sands, and the White Chalk group have all been affected by faulting. You can see there's clearly some sort of offset. What I'm going to show now is I'm going to be using an elevation surface for the White Chalk itself. I'm going to be showing about how borehole coverage will affect what I'll actually find in the ground. So I'm going to be comparing 18 boreholes with 74. So first of all, we can see that there is, at Blackwall Tunnel, there is some sort of north-south trending fault with like a sort of 10-metre displacement to the east, and which is what we know there's a fault anyway there. So I've done something right strip already, which I was quite happy about. And we've got a drift-filled hollow in the northwest corner, which is causing this uplift in the chalk. But when you actually increase the borehole coverage there in the area, you actually realise there's a lot more going on. And it's not just one fault, there's multiple faults. And they're intersecting each other, sort of northwest striking and northeast striking. They're kind of going like that. And what you're seeing is the ground is a lot more complicated. And we can work out more about what's going on with the ground by having greater borehole coverage. Now, that one region is this red dot here. So it's a tiny area, and that had relatively high borehole coverage. And the problem is that most of the London basin doesn't have this sort of thing. So this is going to restrict my fault zone mapping to London itself rather than the London basin. But this isn't an issue, because this is where most of the geotechnical engineering work in the southeast happens. So it's going to still be a benefit to the geotechnical community. So I should have said kind of the idea behind why I wanted to do this was, so if say you, it's trying to do it as like a predictive map. So say if you, your company wanted to do some works, say at this site, they could say, okay, it's likely we're going to have a fault. Or it's likely we're not going to have a fault on site. But this leads me on to the sort of the issues of data. Is that it's like, because the aim of my PhD is to try and better understand these faultings, I want to understand how it's actually affecting the ground engineering. So I want my research to not just be purely academic. It's engineering geology. It's got to benefit the geotechnical community as well. And so in order to do that, I need to be able to get access to good data. So if any of you are ever doing any work on in London and you're having problematic conditions, please get in touch, because it would greatly benefit in my research, and in the long term it will benefit the geotechnical community in London. So to go on to sort of conclusions now, London is being affected by faulting, and it looks to be like it's originating from the basement, and they're propagating up and getting these bands of very intensive faulting. I'm producing a predictive fault map of where these are, so to hopefully identify them in central London. So if you can collaborate in any way, it would greatly benefit us. And sort of this is sort of more the take-home message for people in industries now is, if you've got faulting on site, prepare for unexpected ground conditions. It's going to mechanically weaken the ground locally, and the fracturing will affect its hydrological behaviour. It's going to increase uncertainty, and it needs to be taken seriously. So, thank you very much.
Thanks very much, Tom. We'll now hear from Jonny Neville from MacDonald on asset management.
Brilliant. Thanks, Tom. I was going to start my presentation by saying that I'm going to talk about something quite different, but from the past 5 or 6 presentations, it's not actually that different. But I'm going to talk about asset management and kind of how I've been involved with it, and kind of answer this kind of question of if it is an important piece of the engineering geology jigsaw and vice versa. So a quick run through for my career so far. Started off at school. I actually dropped geology at school, but saw the light, and I'm now doing a career in it. So something changed. I went to do my BSc, did my MSc at Newcastle, and then I joined Mott MacDonald in 2014, where I went straight into the asset management team, and I've recently moved to the engineering geology team. So, and who knows what the future holds for me. But I'm going to focus about my couple of years in the asset management team and what I've kind of learnt from that. So first of all, let's start off with what is asset management. When I came into Mott MacDonald, I didn't have a clue. I'm sure some of you in the room don't know what it is, so I'll try and break it down for you. When we say asset management, the asset is the geology. It's the geology that we all know and love, and asset owners and transport asset owners have to manage their assets to make sure they perform in the way they intended to. So we have 3 types of assets in the transport. We have the embankments, we have the soil cuttings, and we have the rock cuttings. And I've put kind of 3 different transport owners here. We've got the kind of HS1, which is kind of the new, well-designed assets. So then we've got Highways England, where soil mechanics was kind of in its infancy, but it was there. And then we have Network Rail, which was build these railways as fast as possible 150 years ago, literally dumping kind of spoil and whatever they could find to create these embankments. So no compaction and definitely no kind of engineering geology there. So what happens if asset management doesn't happen? Well, a lot of unfortunate things. We've not got a not very happy train here, which is near Oban in Scotland. This actually is quite lucky that those trees are there. This is a 15-metre high embankment, and there is a loch just to the other side of that, so that could have been a lot worse. This train derailed because of a rock fall, and it hit a couple of boulders. Luckily, there was only 8 people with minor injuries who were taken to hospital. We've also got, this is the Hatfield Colliery, where a spoil tip from the colliery has had a rotational failure, and so this is the toe bulge that you can see here. Again, luckily that was spotted by the train drivers before it got to that stage, so very lucky again. I could talk forever about all of these, but in summary, there's probably about 1 or 2 of these kind of events that happen a year. But luckily, very luckily, we've not had kind of a fatality on the rail network since about 1945. So some may say we're due one. Hopefully, touch wood, that's not the case. But this is just to emphasise how important asset management is. It's really dealing with saving lives. Okay, so in the past, we kind of have our engineering geologists and our asset management, and they're very separate. Engineering geology was very much kind of let's design the assets, kind of get a factor of safety above 1. Bob's your uncle, everything's okay. Let's kind of just leave it. And then asset management was kind of the bean counters, the people who have the money and decide what to do with it, but don't really have that engineering geology knowledge to kind of help inform their decisions and prioritise where that money is going to go. So it was very disconnected, and a lot of the money wasn't going where it should do, and we're not kind of making effective use of that money. So I'm just going to talk about one example of asset management in the network rail world. And this is basically to manage the assets. We've come up with a kind of risk matrix, and we've got kind of 2 parameters. We've got the earthworks hazard category, and that is kind of the condition of the asset, A being kind of the best condition, and E being something seriously needs to be done. It's almost going to fall down kind of thing. And this is very much where the engineering geologists come in. And I can't emphasize enough that engineering geology is at the heart of asset management, because, as they say, if you put rubbish in, you're going to get rubbish out. So what we need is examiners going out and looking at these assets. They're kind of looking for, well, measuring, for example, the slope height and the slope angle, maybe looking for precursors of failure, such as tension cracks, and that really needs that kind of engineering geology knowledge to kind of plot it correctly on here to then help work out what asset intervention might happen. So the other parameter is the criticality band, and that is kind of the consequence if that asset was to fail. So, for example, the East Coast Main Line, that's a major route with lots of trains, and if anything happened there, then there could be the high potential for fatalities and would cause major disruption to the line. Whereas if you had a rural, kind of once a day, a train goes past, then you get a kind of lower score of 1. So from these 2, you can plot every single asset on this asset matrix, and then you can come up with the kind of how you're going to manage those assets based on your kind of budget and, I suppose, risk appetite. This is for the soil cuttings for Network Rail. Now, you could, in theory, have everything as renew. If you had unlimited money, you could renew everything and you'd be in a great place. But unfortunately, we're not in that scenario. So you've kind of got to make the best use of the money that is available. And in Network Rail's case, the key aim is to kind of maintain the assets at the steady state. So we're not trying to improve them. We're just trying to keep that factor of safety from decreasing. Okay, so this asset management is very much a balancing act. If we take the car analogy, you could have a good and fast car, but it's not going to be cheap. Or you can have like a fast, and you could do the job fast and cheap, but it might not be very good. But it's important to emphasize you can't have all 3. And that's really a balancing act depending on the client and what their priorities are. Similarly, you can't have a low cost, great service with low risk. You can have 2 of these, so you could have a high cost with some kind of low, with low risk, but maybe I'm getting confused here. So anyway, you get what I mean. So you can't have all three. So it's really a balancing act between the risk, the cost, and the level of service. So this is kind of a little summary of where I feel engineering geology is at present and asset management. As I've said, engineering geology is at the core of asset management. You need to have that understanding of the assets to then help inform decisions about what you're going to do from an intervention standpoint. Now, I've just had, this is kind of the age of the networks and the different, so for Network Rail, Highways England and HS1. And obviously, Network Rail, the assets were never intended to last this long, and now the asset owners are asking engineers to help the assets last longer than they originally intended. So that is creating a challenge in itself. And for new assets such as HS1 and HS2, asset management is very much at the forefront of the design, which is a great thing. So it's very much getting considered at the start and the onset. And so this is how we're getting this new interconnection between engineering geology and asset management. So just to kind of look into the future about where it's going to go, I think the big thing here is technology and how we can use technology to our advantage and kind of understand assets in new ways. So for example, this is some LiDAR imagery taken of the rail network, and the red, this is kind of showing change, and so this is some vegetation growth in this example, but this would be a really effective tool for understanding change, and again, a further tool for working out how to prioritize where that money is going to go. Obviously, with new technology, that's going to bring new challenges of kind of data and big data, processing that data, and making sure that it's a good quality. But it's quite an exciting time for the asset management industry. It's kind of a mix, if to summarise, it's kind of like a mix of geology meets economics, meets technology. And at the end of the day, like I said, you are saving lives. So I don't want to do a little plug, but I am going to do a plug. If you find it quite interesting, I know Chris Power, who's our technical lead, is here today, is always looking for new people who are interested in asset management. So if it's got you interested, you can speak to me or you can speak to Chris after drinks. Yeah, so thank you very much.
That was definitely a plug. Now for our final talk of the evening from Harry Eady from Fugro.
Just trying not to get this remote wrong. So yeah, this is going to be my talk on collapsed ground. And obviously collapsed ground presents quite a significant threat to infrastructure and human health. Maybe not so much in America where these corvettes kind of fell into a giant hole. This is just a good example of what can happen when collapsed ground is not properly identified. So instead of these fantastic locations which you've talked about, I'm going to go back to the north of England where we have our lovely CCGT power station. And this is the proposed SI and building of this station where this talk kind of takes place. Due to the prevalence of collapsed ground that we thought we identified on the site, we initiated a significant site investigation program featuring CPTs, geophysics, and whatever not you want to think about. So this is kind of map of the site. The site area is roughly a quarter of a kilometre squared. And we have this yellow boundary around here, which indicates a British Drilling Association yellow classification, i.e. it's okay to drill. And we have this red area here, which is due to the site's previous use as a former chemical works. So i.e. there should be more care taken around in this location. All of these locations you can see represent 5 years worth of previous historical SI data that were taken on this site before we even came to have presence there. So the stratigraphy at the site is fairly simple. We have a lower Triassic bedrock, followed by a discontinuity, then Holocene superficial deposits, which makes characterization pretty simple. The superficial deposits are characterized by topsoil and made ground, which again is due to the previous use of the chemical works, followed by a series of glacial deposits such as clays and glaciofluvial deposits, which are sands, clays and gravels. We're going to ignore this infill material at the bottom for the moment because I'll get onto that later. The bedrock geology is increasingly simple. We have limestones, mudstones, limestones, and mudstones. So it's quite an easy thing to characterise. We have separated all these horizons out due to their geotechnical properties, which are then used in the modelling stage, which we'll get onto later. For this talk, we're going to particularly focus on the Burlington limestone and the Edlington mudstones, which are large formations present across much of the north of England. So, the issue we had with this site was that we found during the depth study phase there was a potential for gypsum to be present within the borehole stratigraphy and to be localised within the ground. Gypsum is an issue because it has the potential to dissolve, and when it dissolves it forms large cavities within the ground mass. These cavities or voids are weakened zones. So if you place a large load, such as your power station, onto these areas, that might not be stable. Therefore, the life of your infrastructure might not last as long as you'd hoped. So gypsum, we found, existed in giant bands in the mudstones and limestones, and also as constituent minerals within the rock core. Again, with the site's close location to a river with a high water flow potential, this is not really good from an engineering point of view. So we took the previous 5 years' worth of SI data and built it into a preliminary ground model, which you can see here. We have our initial interpretations of our stratigraphic horizons, and in red, which you can't really see, but we have our geohazard zonations, or areas that we thought posed a significant threat to the project, which we've turned into a 2D surface here. So we've geohazard zonated the site before we even began our site investigation. These areas of anomalies were identified due to their unnatural topographic changes on the surfaces, which we deemed couldn't be possible due to natural geological processes. So due to the fact there is a large power station that's being planned and we have these unnatural changes, the clients requested that we did a geophysical survey across the site, which runs across the cooling towers and the main power trains. There's 29 seismic refraction lines that will run across the site, each with around 90 geophones at a 2-metre spacing, and you do some triangulation and you get about a 30-metre penetrative depth of the seismic refraction. And the results of the lines look quite like this. This is a seismic refraction tomographic plot, and as you can see here, it's quite complicated. But we have our chainage number along the bottom and a depth in here. So between 0 and 20 metres, we have our superficials and mudstones. Between 20 and 35, where it kind of cut off, is the Burlington Formation. Within the Burlington Formation, you can see quite clearly that it sags here, which we indicate may be a sign that collapsed ground might exist on the site, due to this unnatural sagging identified by geophysics. We found 42 zones of where this kind of plot existed. So really, you can see that's quite a high potential for these anomalies or collapsed zones to occur on the site. Again, which is very bad if you're trying to build all of your infrastructure there. And most worryingly, the main power train, the northern one, had the largest anomaly at the top. So this is something that we need to identify. It's also fair to say that as geophysics lines did not run across all of the site, there may be other zones of collapse that which haven't identified through geophysics, which is why we had to adapt our site investigation program to adequately pick these up. To do this, we used a dynamic site investigation program. This basically works by taking our previous depth study model, which you saw earlier, integrating all the available data we had at that point, and telling the drilling rigs to move to the areas that we thought posed the most threat. Then whilst drilling is taking place, you feed that data straight into a ground model which already exists. So this is while the data comes straight off site, you put it into another ground model. Effectively, you're building up this 3D model as the drilling is going on and informing drilling locations. And eventually, once the SI program has been completed, or for whatever reason you want to stop the SI works, you'll have a fully dynamical and developed geohazard assessment, which is the kind of stage we're at now with this project. So this SI program featured around 20 cable percussion locations to around the depth of about 30 metres. So this really penetrated the top of the mudstones and not much further beyond that because of the natural hard nature. It featured 40 locations which were continued with rotary coring techniques to around a maximum depth of about 100 metres. And then a further 176 CPT locations were implemented across the site, again to prove rockhead and to define the superficial deposits. These CPTs were also fitted with a different number of techniques such as magnetometers for UXO surveys and also MIPS to detect hydrocarbons in this area. So I'm just going to scroll back 2 slides. We have our largest anomaly, as I showed you here from our geophysics plot. We have borehole 1 and borehole 1B. So we're going to have a look at what the core looks like in those areas to see, can the core show us if collapsed ground exists? So we're going to look at depths of around 31 to 33 metres. And first, in borehole 1B, you can see that it's fairly competent. It's solid core, and there's no reason to concern, really. That would take the load of a power station quite nicely, provided it's not too fractured and it's not crumbled. The fractures that exist within the core are bedding fractures, which are pretty good because you expect when the core is taken from the ground, expansion would occur, and these strata parallel bedding fractures just are simply as a stress release. However, you may be able to see it on this screen, but it started to go quite brown here and quite broken up. This is the early signs of dissolution of the gypsum as it's being dissolved. This brown colour and the voguing that is occurring is simply the result of the gypsum starting to basically vanish from the core, and therefore making it start to go quite weak. Moving 20 metres away, we get to borehole 1. At the same depth, this is the same limestone, and we see that it's completely different. There's large areas of core loss within this area, which is simply where the drill has not recovered any core because it's all too crumbled. There's too many fractures, and basically there's no core recovery. Again, this is a bad sign because obviously this is showing if you try to put any load onto that, you're going to have a bad situation. You can see the red lines here. These are the reinterpreted fracture lines that are taken from the core, and they're more high-angled. These don't represent bedding fractures. These are a result of shearing or movement that's happened in the core, indicating that this rock has vertically moved in its own position after deposition, i.e. there is some collapse occurring. And again, the whole core, I've just highlighted this box, but the whole core is attributing features which show dissolution. It's going brown, there's vugs are forming. So we are going to say that this core is the result of dissolution occurring within this core, or i.e. in this collapsed ground. This is a very busy slide, so I'll try my best to kind of explain this. But this is data taken from a discontinuity logging, as you do the solid core logging at site. At the bottom, we have fracture indices, which is the number of fractures that occur within a given space. So the higher the fractures, generally the worst. And we're seeing borehole 1A, with these blue dots here, have quite a high fracture indices profile, which means that there's lots of fractures occurring in a small given time, which is expected with a core which looks so bad as the one you've just seen. These horizontal lines here represent areas of core loss and non-intact core, which, as you can see, is quite intense between 20 and 40 metres within the Burlington formation. It's much more pronounced than in borehole 1B, and that's attributed also to the loss of core quality in RQD on the side, or rock quality designation, or solid core that's less than 10 centimetres in length. So we can attribute core loss to a loss of RQD. And finally, the fractures in the core, in borehole 1, as I showed you earlier in the core, are more high angled than in borehole 1B. Indicating borehole 1B's, the fractures are bedding fractures from expansion of the core, where this is fracturing due to shearing and movement within the core, or within the rock mass as it's in situ. Finally, the last piece of evidence for collapsed ground is the infill material that occurs. This was at the base of the superficial deposits. It's actually an auto-jumbling of the gravels, clays and sands in the superficials above. This is only a result of collapsed ground which occurs below, and the whole rock mass is moving, which allows an auto-jumbling of material. This is not occurring during deposition, this is after deposition of the material. So we can attribute where areas we have infill material, this might be an indicator that we have some collapsed ground below. So you could move a CPT, you could do shallow boreholes, and you could think, actually, I need to investigate deeper because there's could be something lying beneath. This is particularly applicable on this site because our client originally only wanted to drill to 30 metres. However, all of the collapsed ground we have found is roughly around 60, 40 metres beneath the ground. If we had not found these indicators, they would not have found any collapse signs, which could have been bad for the life of their project. Building all this into a 3D ground model, this is an interim stage, this hasn't been finalised yet, but we can start to see some trends that are occurring. These red areas indicate areas of collapse, which we have identified as being our zones of core loss, zones of dissolution, whatever you want to call it. And we can see that they predominantly exist within these areas that we identified in the geophysics. However, we've been now able to morphometrically analyse these because we've placed drilling rigs, CPTs on site to be able to quantify what is going on. We're not going to say that the geophysics has proven that all of them are collapsed grounds. There are some natural anomalies that occur within the grounds, which is why not all of the geophysics areas have signs of collapsed ground. And as I said earlier, we identified through modelling and rotary techniques on site that there's some collapsed ground areas that occur which aren't identified with geophysics. This is due to the fact that geophysics only has a depth of around 30 metres. And finally, we also have, this is our what's called a voxel model of what's going on in the core. We have our well sticks that go down here, and these areas of red indicate zones of core loss. This is occurring in the lower Edlington formation, and what we're actually seeing is core loss in the Edlington is providing sagging as a loss of material in the Brotherton, which is then associated to all of the collapse and brecciation that is occurring. So we're actually finding the whole profile of material at this site is subject to intense dissolution, intense core loss, which is causing a generic sagging of the whole bedrock, which, again, when you're trying to load a power station on top of it, probably won't do well for the infrastructure. So, in conclusion, gypsum has the potential to weaken the ground and allow large cavities to form. Ground modelling at an early stage may be beneficial because it allows you to identify these potential collapse areas. Geophysics can be a powerful tool for the early identification of the geohazard, so you can move your site investigation and plant equipment onto the site properly. Dynamic site investigation will allow you to characterise the site fully to all your extent, and the core analysis can truly reveal what is going on in the ground. That's fairly self-explanatory, but the use of a final ground model may help you take it into engineering assessments in the future so you can properly design your foundations around the presence of things that are in the ground. And that's it. So thank you, and I look forward to any questions.
Thanks very much, guys. All those presentations were really interesting. I'm sure everyone will agree the variety and the technical content was fantastic. Just before we go through for the sponsored drinks and a couple of questions, I'm sure, for our presenters, I'm just going to run through a few upcoming events. So on the 16th of May, we've got Peter Braham speaking on heat from abandoned mine water. That will be a venue that's still to be confirmed. We think it's going to be in Leeds, so we look to move away from the southeast for a bit. Then we've got, on the 13th of June, a day meeting, Offshore Engineering Geology, Geomorphology and Geohazards. That's a working party that Chris Martin is developing, and that's going to be here at Burlington House, so registration's open, so please get involved with that one. And then in July, on the 18th, we'll be out Wallingford Way at Fugro's offices, and Simon Price will be talking about some of his research from his time at University of Cambridge, Britain's icy past implications for ground engineering. And now I'm just going to pass over to Tracy, who's going to introduce our new format for the Glossop Award.
Yes, we wanted to really launch this tonight on the Early Careers event. So the Glossop Award typically has been for an early career engineering geologist under the age of 30 to come and present on a topic as part of their career. One of the things that we are finding is that actually, as we look at people's careers, and their careers are changing, and they might be working on a whole variety of projects, and they could be quite small, they could equally be working as, say, one small cog in a massive project, and so therefore it can be quite hard for people to be able to submit an application under the Glossop criteria. So we're looking at changing this, and this is what we've put forward. So we're asking, it's still for under 30s, so again, you know, put out to yourselves and people in your company, and we're asking for a sort of a synopsis, and this will obviously change each year. So what we've put forward this year is what role will technology play in the future of engineering geology? And just listening to some of the presentations today, we could sort of see where this is starting to influence our work. And you guys are the future of the industry, so it would be really useful for you to be actually be able to impart your thoughts and knowledge to the engineering geology profession as to what you see going forward. We'd also like to hear a little bit about your career. So I know, again, some of you have already sort of included that. So this is what we're also asking. So just a review of what people have undertaken. And the other thing is that what we're looking for is actually to then invite the winner onto the committee if they want to. It's optional. It's not a mandatory, you shall. But we'd like to hear actually what is it that you would like to be able to do if you had a position on the committee. So just be able to sort of, you know, just put down sort of some words as to actually what you think we could be doing as a profession, reaching out through the companies to move ourselves forward. And also your CV. So you can see it's worthwhile, £500, that's not bad. So we'll be getting this up on the website with the application form, but it would really be great if you can go back to your companies and tell everybody about this. So hopefully we can get some good applications in. Fantastic. Cool. Okie dokie. Tell her why.